Hey folks, in this video we're going to talk about magnetic forces between two wires that are carrying current. Okay, so the first example is very simple. Let's say we have an individual wire carrying a current to the right. Okay, so there's our current. Well, as we've learned in the last couple discussions, that current makes a magnetic field around it. And if you use your first right-hand rule, meaning your thumb points to the right, your fingers curl with the field, the magnetic field wraps around the wire, and the magnetic field comes out of the page when you're above the wire, and it gets weaker as you get farther away. And then that magnetic field goes into the page when you're below the wire, like so. Okay, so we have a magnetic field made by that wire, and that magnetic field, we used Ampere's law to calculate that. So we'll call that B1. That equals mu naught I over 2 pi radius. All right, so that's your magnetic field strength as you step away from the wire. What happens if we put a second wire in that magnetic field? We'll call that I2. Okay, well, now you are placing a current into an already existing magnetic field. So that current will experience a force, and we've already learned about the force rule in the previous chapter. We'll call that F2. That equals that current, I2, times the length of the wire cross B made by 1. Okay. Now, so then you can rewrite this. You can say force 2 equals I2 times the length of that wire times B1, which is mu naught I over 2 pi r. Now, I kind of lost the cross product there because I2 is perpendicular to field 1, okay? And then often in a textbook, you'll see this shortcutted. It'll look like this, mu naught I1, I2 times the length of the wire over 2 pi r. R being how far apart the wires are, okay? So that's the force, F2, acting on wire 2. Now, which way will that force be? Okay, well, if you imagine you use your force right-hand rule, your Lorentz force rule. So for I2, you stick your fingers to the right, your hand points to the right, and that magnetic field that we drew is into the page. So you curl your fingers into the page. Your thumb will point up. So there'll be a force. That'll be the force acting on wire 2. Now, if you were to repeat this process for I1, and I'll put an I1 there for us. There's your I1. You would get the exact same answer, okay? In other words, F1 would point down, and it would be the exact same magnitude. These would be equal and opposite forces. Does that sound familiar? It's Newton's third law, right? If I1 pulls on I2, I2 pulls on I1, and you would get the exact same answer here, okay? Now, something else you might notice in some textbooks is they'll take this equation, divide both sides by L. So they'll say the force per length equals, and then you've got everything else in there, mu naught I1, I2 over 2 pi r. So they might say how many newtons per meter will the wires experience, how much force, okay? Now, a quick note about this. Normally when you turn stuff on in your house, like electronic devices or whatever, you plug a lamp in or something, you don't see wires pulling on each other, right? Okay, or pushing on each other. Oh, and by the way, let me make a quick note of that. What if the wires are going opposite directions? What if I1 is this way, and what if I2 is that way? Okay, well, if you have that, then the wires will repel each other. So that'll be force 1, and that'll be force 2. And again, those will be equal and opposite. So just a quick note on that. So, but you don't normally see this effect, right? When you turn a flashlight on or you plug a lamp in or whatever. Okay, so what's going on here? Well, it turns out if you do the math on this, you have to have some awfully big currents to get an appreciable force that you can actually notice. Now, I got a quick video clip. This is from the Mechanical Universe series, and by the way, I highly recommend that series. It's awesome. But in this clip, you're going to see a car battery manufacturing plant. Okay, so let me skip over to that. So. And this is the video called "The Electric Battery," and again, it's part of the Mechanical University series. It's awesome. Okay, so these are car batteries being manufactured, and let me explain what you're going to see. You're going to see a technician put jumper cables onto one of these and charge it up, meaning just run a large current through it. Okay, so
he put two electrodes of the same metal, lead, into an electrolyte,
And I want you to
a
watch
weak
the
solution
jumper
of
cable
sulfuric
wire
acid.
when you see it.
Then he applied a voltage between the electrodes, driving electric current through the solution.
All right, here it comes. All right, so here's the
This had
battery
the effect of
manufacturer.
oxidizing one electrode, changing its work function.
Okay, so you have these two jumper cables. Current's going to go into one and out the other. So currents are going the opposite way. So when the current turns on, they should repel. And you'll see some numbers change on the panel here when the boom, those two wires are now repelling each other. That's what's causing these two wires to push apart like that. So this current is several hundred amps of current. So that's why you actually notice that effect. And when the current shuts off.
After that, the principle's the same as Volta's pile, but this battery had a great.
Okay, so after the current shuts off, the wires go back together. So when you have a large current, then you can see the wires pushing or pulling on each other. Okay. Now I do have one more example for you involving forces between two wires. Here the wires are running parallel to each other. Well, what if they're running perpendicular to each other? So what if I have, let's say I1 going like that, and let's say I have a segment of wire, we'll call that I2 going like that. Let's say this distance here is A, and let's say the length of this little wire segment is B. What's the force on I2? Okay, so we know that the magnetic field made by B1 is still mu naught I1 over 2 pi r, but now we have a problem. That magnetic field is going to vary. Okay, if I draw that magnetic field, you'd have dots over here. That's magnetic field coming out of the page, but it gets weaker as you get farther away from the wire. Same thing over here. You got a magnetic field into the page, but oh no, that field gets weaker as you get farther from the wire. So that B1 changes. So you guessed it, we're going to have to do some integration here. Okay, so we know the force on 2, okay, would be I2L cross B, all right, if wire 2 is parallel to the field. Well, it's not. So what we have to do is look at a little chunk of the wire at a time. We're going to call that distance dr, okay, and it's going to have a little chunk of the current, or it's going to have the current I2. So we're going to say that's df2. Okay, so df2, and we are going to set that equal to I2 times, it would be dl, but because it's the same as dr, we're going to call that dr cross B1. Okay, and I will sub in the expression for B1, which is mu naught I1 over 2 pi r. And then we're going to integrate this. We're going to integrate this from the beginning of that wire is A away from wire 1, and the end of that wire is A plus B away from that wire. And if you look at the right side, the only variable over there is dr over r. So if I rewrite this, okay, so we're going to integrate df, okay, equals the integral from, and I really should have, these limits should really go on the right side. Sorry about that. They really shouldn't go there. All right, so the radius goes from A to A plus B. Oh, and I'll put everything that's a constant out front. We've got a mu naught, we've got an I1, we've got an I2 over 2 pi, and what we're actually integrating is simply dr over r. Okay, that's our variable there. Okay, so if we integrate this, we get F2 equals mu naught I1 I2 over 2 pi, and the integral of dr over r is natural log of r, and we have to evaluate that from A to A plus B. Okay, that's an A right there, not a 0. And if you do that, you get mu naught I1 I2 over 2 pi natural log of A plus B over A. Okay, so that is force 2. And would it be attract or repel? Okay, well, if you go up here, if you use your Lorentz force rule, current's moving to the right, so you point your hand to the right, our fingers curl into the page, so that force would be up. Okay, so there would be an upward force, F2, on this wire. Now you might ask yourself, well, how would I calculate the force on wire 1? What's force 1? Well, the forces have to be equal and opposite, so this force would be F1, and it would be down, and it would be the exact same magnitude as this. Okay, so that's the shortcut for calculating F1, even though Newton's third law. For every force, there's an equal and opposite reaction force. All right, so I hope that video was helpful, and I got one more example in the next video looking at like a three-dimensional view of some of these. So hope that was helpful, and thank you very much.